Today I'm going to tell you about the placement advertising fraud in mobile app and the technical challenge we have faced in designing a system to detect this kind of placement fraud, and also about how prevalence this fraud in mobile app. So to understand the ad fraud, we need to first understand the mobile ad ecosystem. So although most of mobile apps seem to be free, this is actually not the case, because free apps actually depend on the advertisement to earn the revenue for developers. So there are three players in the ecosystem. First is the app developer, then is the app user, and also the ad network. So developer embed ads in their app, and to do so, an app developer needs to first register himself with a mobile ad network, such as Microsoft Advertising. And the ad network provides the developer with an ad plugin. And the developer includes this ad plugin in her app. So when a user uses this app, so the ad plugin can fetch ads from the ad network and display it to the user. So the ad network selects ads for the user based on many factors, so like the location of the user or the user's inferred interests, and so on. So when users see or click this ad, the ad network actually pay developer. So specifically, depending on the ad network, developers get paid based on the number of ads delivered to user or the number of clicks by users. So or sometimes it's a combination of the two. So therefore, in this setting, developer of free app have incentive to commit ad fraud. So for example, they can change the way as displayed in order to increase the possibility of user accidentally click an ad. So in general, ad fraud costs the ad network a lot of money. This is just because mobile marketplaces nowadays are very, very large. So till the end of last year, so over 1 million apps have been released on Google Play and Apple App Store. And many of these apps are ad-supported and rely on ad networks for revenue. So several recent studies have pointed out that advertising in mobile app is plagued by various types of ad fraud. So when fraud happens, ad network actually lose money. So specifically, ad network are estimated to lose nearly $1 billion, so which is around 12% of the total mobile ad budget in 2013 due to this fraud. So for mobile apps, one kind of fraud that is commonly seen, at least by Microsoft, is called placement fraud. And in this paper, we study detection methods for placement fraud. So, and how can developer commit placement fraud? So they can either change the layout of an ad in order to increase the chances that a user accidentally clicks the ad. Or they can deliver an ad but not display it in the visible area of the app page. And in this case, the ad network thinks an impression has been generated, but it has not. So ad network prohibits this kind of behavior. So in the legally binding terms and conditions that developers are required to sign, for example, Microsoft Advertising says that a developer cannot manipulate ads in any way. So we now give an example of this kind of fraud. So our first example is that of an intrusive ad, and we call it an intrusive ad. So in this app, which contains programming language tutorial, each square in the page shown can be clicked to access a tutorial of a subtopic. And in this intrusive ad example, so the ad is placed in a way that covers up a normal button. So the next example is called many ads, so in which an app page contains too many ads than permitted. So for example, Microsoft Advertising allow at most one ad per phone screen, but in this example, so the page contains 3 ads. So the final case shows how ads are hidden behind other control. So in the first example, an ad is hidden behind some play cards and is invisible at the beginning of the game. So, but in this game, the play cards cover up the ad will gradually disappear with user click. So which means in a certain stage, it is very possible for a user to generate an accidental click. So in the second example, an ad served by Microsoft Advertising is hidden behind a banner from the app developer. So, and if we remove the banner, the page should look like this. Yeah. And in this case, the developer seems to be trying to give the impression of at least an ad-free app, but while benefiting from the impression actually generated by the Microsoft side. So today, ad network rely on manual inspection and other trigger to detect those shown placement ad fraud. But this method can be error-prone and require much manual labor. Specifically, it usually takes several tens of minutes to 1 hour to only scan one app manually. And what's worse is that a human cannot detect some types of placement ad fraud. Like the hidden as violation we have shown before. So therefore, the main goal of our work is very simple. It's just to try to design an automated system for detecting placement ad fraud in mobile app. So to achieve this goal, we face 2 challenges. And the first challenge is to answer how to scale the automated system to thousands of visual complex apps. So as within an app can appear on any page, and apps can definitely have many pages. And the complexity of detecting ad fraud depends upon the number of UI elements on each page. So for example, to find an intrusive ad or hidden ad, one may need to explore every visual element in every pages. The visual layout of a single page can be complex. Specifically, there can be tens to even 100 clickable elements in a single app page. And in addition, it is possible for an app to have a potentially infinite number of pages. To give this example, just consider a news app. The news list can be updated every several minutes, resulting in many, many distinct pages. Especially for tablet app, and this characteristic of app can actually lead to a very large search space. It may be necessary to sacrifice search completeness in order to achieve scalability. The second challenge is how to accurately and quickly identify fraud. And this analysis is actually more challenging than it seems. For example, in some tablet app, the app page size can be larger than the viewing area. It's called the panoramic page. And in the shown figure, with scrolling, the user in turn sees 3 different screens. However, there is no ad in the first 2 screens, and the user will only see 1 ad in the 3rd screen. Therefore, while the page may contain multiple ads, as long as any possible viewing area contains no more than the permitted number of ads, this app is not committing fraud. And detecting whether a fraudulent viewing area configuration exists is known as the sliding screen problem. Also, another example is that in some mobile OS, there is no depth information like the coordinate associated with UI elements. This makes it hard to detect the hidden ads. Because we need to infer the depth information. To overcome this challenge, the traditional method maybe uses static analysis, but apps can defeat this analysis using dynamically create an ad during runtime. Therefore, our method uses dynamic analysis. It checks for ad fraud by actually running the app and using an UI automation framework, and in which each app can be navigated by simulating UI element actions like the button click or scrolling bar, swiping scrolling bar. To deal with the visual complexity, we develop scalable techniques to navigate app pages without instrumenting the app or assuming any prior knowledge of the app structure. And to achieve the accurate fraud detection, we design efficient algorithm for each type of fraud. And our paper makes 3 contributions. First, we have designed and implemented an automated system called DECAF. That contains scalable app navigation and efficient fraud checker. And second, we have characterized the prevalence of placement fraud by analyzing 50,000 phone app and 1150 tablet app using DECAF. And the system has been already used at Microsoft to detect placement ad fraud. And the fraudulent publisher are contacted to fix the problem. And the app whose publisher actually didn't cooperate with such notices has been blacklisted and denied ad delivery. I will now discuss the DECAF system. The input to DECAF is an app, and within DECAF there are actually 2 components. The automated UI navigation component, which is also known as a monkey. and a series of fraud checker. So given an app as input, DECAF runs the mobile app in an emulator and interacts with the app by clicking button or other UI action. So these clicks can trigger visits to different app pages. And in each app page, the DECAF runs fraud checker and examines page content and layout for placement ad fraud. So the output of DECAF is a detailed report that lists whether or not an app page may contain the placement fraud. So in our example, so a many ads fraud has been detected in the first page and hidden ads has been detected in the third page. So I'm now going to first describe the design of the UI automation component, the monkey part. So the monkey interacts with the app through two channels. First is the UI extraction channel, and second is an UI action channel. So an UI extraction channel is for extracting UI element and their layout in the current page of an app. So as you may see, it is shown as an UI structure tree in the page. And this is how we represent a page, so in our system. So once the monkey extracts the UI structure, it knows which UI elements are in the page. So the monkey has an action dictionary that lists the action to perform for each type of UI element. And it also keeps a set of previously visited pages as a history. So the monkey may decide to click a button on the current page based on these two things. So in our example, by clicking the continue button and this clicking action is actually delivered through the UI action channel, and this behavior causes the next page to be visited. So the whole process repeats across each clickable element in every page, in a normal monkey. So the monkey itself is conceptually straightforward, but there are two problems worth addressing. And the first problem is how to reduce the search space. So one obvious method is just try to reduce the space is to remember all the previously visited pages and avoid clicking UI element on previously visited pages. It's just like maintain a global graph. So however, the problem is that the number of distinct pages can be practically infinite. So for example, this is a UI page of the Reddit app, and in this page, click the post list can lead you to a distinct page. But the problem is the post list is updated every 1 minute. So when this page is, this post list page is revisited, since the content are different, so it's already a different page from the previous visited one. So to reduce the search space, our paper makes the following important observation. So for placement fraud, it is sufficient to consider two pages as equivalent if their UI structure is similar. So thus two pages can be structurally similar even if their content is different. So for example, the post list page in the Reddit app needs to only be visited once. So even though the content of the specific post list may be different in different visits. So now let's see some example of structurally similar pages. So in this page, there are two groups of buttons. And click any button in the glue group can lead you to a similar page that has an image, a text box, a clickable menu list, and an ad. So all the buttons clicked in this group can lead you to structurally similar pages. And similarly, clicking the right button on the right side leads you to structurally similar pages. So although they may show different one bottle with different prices, but they are considered to be structurally similar since they have similar UI layout. So how can we write an algorithm to define structural similarity? So the intuition for this comes from the observation that two pages are structurally similar if they have similar UI hierarchy tree. So this example shows two pages whose UI hierarchy tree differs only slightly by one button. And we consider them as structurally similar. So, and these two pages are structurally dissimilar. So even though their UI hierarchy have the same shape, so because the corresponding elements in each hierarchy are different. So for example, the first UI element is a text box in page 1, but a button in page 3. And the second is an image in page 1, but a button in page 3, and so on. And to numerically measure structure similarity, we represent each UI structure tree using a feature vector which encodes each type of UI element and position in hierarchy. So for example, the UI tree shown has 2 levels, and we first encode level 1 and then encode level 2. And the final feature vector contains the encoding from all levels of the tree. So when we have obtained 2 feature vectors from 2 UI tree, so we use the cosine similarity metric to decide whether they are similar. So, I mean, as known, so since we use cosine similarity, so user need to specify a similarity threshold that defines when or to what level 2 pages are considered to be structurally similar. So another problem that limits the scalability of the monkey is that the monkey can waste time by visiting previously visited pages. So in this example, in page 1, clicking either button 1 or button 2 can lead you to the same page 2. And if the monkey knows the button 2 leads to page 2, it can avoid clicking it. So, but the alternative is just to click button 2 and then backtrack to page 1. And however, so as discussed in the paper, so in any way, the backtracking can take actual time and sometimes may even up to several minutes. So for example, in this app, remember that 2 different buttons lead to structurally similar pages. Then we ask, to avoid the high cost of backtracking, can we try to predict if 2 buttons on page lead to structurally similar pages? So that in the last example, we can avoid clicking button 2 instead of backtracking. So to predict whether 2 buttons lead to structurally similar pages, we train a machine learning classifier. And the key idea behind the approach is that 2 buttons that have a similar UI hierarchy neighborhood are likely to lead to structurally similar pages. And the detail of the method is in the paper. So having talked about UI navigation, I will now briefly talk about fraud checker. And fraud checker works as follows. Each time the monkey visits a page, the UI hierarchy of the page is input to a series of fraud checker. And this table shows a list of fraud checker we have implemented together with a summary of how they work. So for example, for smaller ads, the checker compares the actual display size of the ad with the minimal violate size to capture the violation. And there's one thing is very interesting is about the fraud checker, about the many ads. So many surface tablet has, so as we said, the panoramic ads, and this page are bigger than the screen of the tablet. So, and we also have said the sliding screen problem is the challenge. So this is another example. So this example shows a screen position in a large page that there are no ads. And as we pan the page horizontally, here is a view that contains 2 ads. So a naive method would just check all possible screen position in the page and see if there is any violation at any position. And in fact, we have designed an efficient algorithm to detect the many ad fraud, and the details please also refer to the paper. So in addition, we have also explored some other optimization like the state importance assessment to further reduce the number of pages. And also we use rendering order inference and proxy assist screen analysis to efficiently detect hidden ads. And this please refer to the paper. So finally, I will briefly discuss some evaluation results. So to evaluate DECAF, we run DECAF on a number of apps and run each app for 20 minutes. And one important goal of the evaluation is to quantify the benefits of scalability improvements using structural similarity and using the classifier we have mentioned to avoid previously visited pages. And to do so, we measure the fraction of structurally different pages the monkey visits compared with the ground truth obtained from real user. So since ground truth needs to be collected from a human user, this process is not scalable. So we limit our study to the 100 top free tablet app. So in this paper, we have also get the second evaluation is to characterize the placement ad fraud in the app marketing. So for this, we run DECAF on 50,000 phone app and 1150 tablet app and study how prevalent different kinds of fraud are and how fraud types depend on the rating of an app or the identity of the app publisher. So to evaluate the effectiveness of classifier-based structure page equivalent prediction, we use a basic monkey that doesn't do any prediction and realize a structure page is equivalent only after visiting it and backtracking. And we also use a classifier enhanced monkey, so with the prediction enable. So in general, we see very good coverage improvement from the classifier enhanced monkey. So there are 71 apps finished with the classifier enhanced monkey, but only 30 finished with the basic monkey. So, and there are 29 apps that cannot finish in 20 minutes. So this is either due to the monkey cannot recognize some clickable elements, or there's some scenario needs the password or username that the current monkey cannot handle, or just some app simply have a very large set of structure page and the monkey cannot finish within 20 minutes. And we also characterize fraud by types, and this is the general results. So we do see some difference, like the hidden as actually more prevalent on the phone, which has a smaller screen of displaying content, so that developer may put more functional button and in this page. And the intrusive ads is more relevant, is more prevalent on the tablet, which has richer control to be used to trigger the accidental click. And for characterizing fraud by rating, so rating value are rounded to a number from 1 to 5, and this shows our result. So in general, what we found is that fraud level doesn't seem to depend on rating, and fraud and non-fraud app have nearly the same rating value distribution. And finally, so each app is developed by a publisher, and a single publisher may publish more than one app. And we have examined how instances of ads are distributed across different publisher. This plot shows our result, and what we found is that so actually a small number of publishers are responsible for most of the ad fraud. So finally, our work is motivated by the observation that mobile ad fraud is a $1 million business, and we indeed need this tool to detect such kind of fraud. And so in this paper, we have proposed DECAF to perform accurate placement ad fraud detection automatically. And our case study of more than 50,000 apps have shown some interesting observation. Yeah.
Okay. Very interesting work. This is Haibo from Shanghai Jiaotong University. So, are you assuming that DECAF can correctly extract all UI actions? Because there are some customized UI which the developer provided to enhance the experience.
Yeah. We don't make that assumption. Yeah, there's indeed some app, and as you said, some customer control we cannot recognize. So, for example, there's one image button, but some user prefer to use an image, but then add something. And the monkey currently cannot recognize that one. But I believe it's mostly the problem from the Windows automation framework. If the Windows automation framework can be improved, then the monkey and the DECAF system can do better. Yeah.
Okay. Thank you.
Will you detect a fraud if the publisher uses ads from different providers?
No. So it depends. So because different provider usually has a different rule or policies.
Right.
So and for detect ad fraud, you need to. So at least for our method, we design sub checker for each type of ad fraud. So I would say if another advertiser has the similar policy, and the DECAF can do that. But if they have a different policy, then we may need to extend the sub checker.
So if they combine, say, Microsoft advertisement with Google ones, it won't be considered as a fraud on one page.
Yeah, this is also tricky. So since for example, Microsoft may allow like one ad per page, but Google may allow 2 ads per page. And anyway, you need to extend, and by design, new sub checker. Yeah.
I was wondering how, or rather, I'm curious how application developers will now try to bypass your system. In particular, since you use a monkey, I'm thinking of something like a CAPTCHA. If you use a CAPTCHA, your monkey doesn't work anymore, it seems.
Use a CAPTCHA.
So, type in 3 numbers that you see, only then I go to the next screen.
Yeah, it may be possible, but at least now, so okay, there's 2 aspects. The first aspect is the sub checker can always be improved. That means if users get some smarter method to bypass the current checking, and we can design the new checker. And the second point is like Microsoft actually they are now doing one thing is to design smarter ad control itself. That means all the checking we are do can actually be performed by our ad control.
I'm less worried about the checker, more about the monkey.
Yes.
So the monkey basically doesn't make much progress.
No, the monkey actually actually focus. Compared with the existing work, we are actually more focused on the speed. How can we browsing actually structurally different pages within a short time? And I think it's already get a big improvement compared with the other work and in the mobile computing. Yeah.
Okay, thanks.
Okay. So is there a reason you use structural similarity? Can't you use the page class instead to detect?
Yeah, you want to use page cluster, and you need to define something to still. So this is just one way to define structural similarity. You can definitely figure out the other way.
Right. The class seems like the more natural thing to me, right? Because if it's the same class, so if it's 2 post pages on Reddit, they will have different posts, but they will be the same class.
You mean template, yeah?
No, like the
okay, page class. Anyway, I know what you mean. Yes, this is because if you see some app, we consider that. I guess you mentioned that so there may be some file there, and each file is one class. Whether we can try to identify whether a page instance belongs to a specific class. Yeah. So, but that one is if you see the app. So, many times the developer only use one page class, and the page class can be dynamically changed a lot of. So, like if you see the Reddit app, they actually only have 2 or 3 instances, but the page can up to 20 or 30. Still dynamic browsing and try to compare in runtime is necessary. Yeah.
Okay. Thanks.
Okay.